All right, I put the solution from today's demonstration on PowerPoint, so let's look what we have. What is the torque on a 25 kilogram door that measures 12 meters across and has a person pushing on it at the edge with a force of 18.2 newtons? Simple torque problem. Torque is equal to force times the radius. The force, of course, is 18.2 newtons. The radius is 1.2 meters across. A lot of students are thinking that the radius of the door is in the middle somewhere. No, that's not the radius of the door. This is a door that's swinging on its hinge. So the radius means the pivot point to the end of whatever's being swung. So in this case, once again, the radius is not half the door. The radius is the pivot point to the outside. So this is R. R is not to the center of the door. A lot of people making a mistake. I wasn't sure what they meant earlier. So it's force times radius, which is 18.2 times 1.2 is 21.8. Next it says, how quickly will the door accelerate? If you remember from your formulas, torque is equal to moment of inertia times alpha, alpha being angular acceleration. So do we know the torque? We know that from problem number 1. Do we know the moment of inertia? You have to go to your book and look up the pictures where they show the moment of inertia for a thin rod on a pivot point that's pivoting this way. This is pivot point, is defined as I is equal to 1/3 m mass times L, the length of the door, squared. So I merely substitute these in. I rearrange the equation. How do I do it? I divide both sides by I. I's cancel. I land up with alpha is equal to torque over moment of inertia. I substitute in again. What is torque? Force times radius. We already figured that out, so I didn't have to really write that, but I did anyway. Divided by 1/3 ml squared. For problem number 1, 21.8 Newton meters, divided by 1/3 times the mass, 25 kilograms, times, again, the length of the door this way. This time they're calling this length, which is still, basically the radius of the swinging door. We land up with 1.8 Newton meters, kilograms, meters. Now this is a mess. So I'm going to let you figure that out on your own. Remember, newtons is really kilograms, meters per second squared. If you watch, what happens is the kilograms will cancel out, the meters will cancel out, and you'll be left with seconds squared. It'd be emptiness over seconds squared. This is what you end up with. But don't forget, when you're dealing with angles, you can always throw in the word radians. So you land up with radians per second squared. Let's look at number 3 really quick. How fast will the door be rotating? This is straight out of the book. The angular acceleration is equal to the change in the angular speed over time. You can rewrite this. Angular final minus angular initial, time finals minus time initial. We know that these two, we start the stopwatch at 0, fine. We start the stopwatch at 0. We start the measurement of the angle at 0. So really all you're writing is angular velocity over time. So basically you can just, don't listen to any of that, just take the shortcut here, since the initial is 0 and the final is 0. Rewrite this. How do we rearrange it? We want to find omega by itself, so we simply multiply t by both sides, and we land up with alpha t is equal to omega. That's 1.8 radians per second. Again, this we solved in problem number 2, 1.8, and this is the time. Multiply them together, you get 1.4 radians per second, because that square cancels with that s. So you have radians per second, not per second squared. Number 4, how fast will the handle be moving if it's located 8 centimeters from the edge? Here's your door. Here are the hinges. The door is swinging like this. Here's the doorknob. If it's 1.2 meters across, and I tell you that the doorknob is 8 centimeters from the edge, you just subtract 8 centimeters. So the answer is the doorknob is 1.2 1.2 meters from the edge of the door. That's your new radius. Not 1.2, because I'm not asking you the speed of the edge of the door. I'm asking you the speed of the doorknob, which is closer to the pivot point. So velocity, this is from your book. Velocity is equal to radius times the angular velocity. We saw the angular velocity in the last problem, problem number 3. We put it here. The new radius that we're looking at, where the doorknob is 1.2. And we land up with 0.8 meters per second. Oh, that seems a little off. Should be a higher number than that, huh? Try again. 1.12 times 1.4 equals, it's 1.56. We land up with radians, meters per second for velocity. If I ask you something that's velocity, say, well, he was running at 1.57 radians meters second. Remember, radians can just disappear. So if we're talking about velocity, and that's just regular old straight line velocity, you can always just scratch out the radians. You can't do that with degrees. You can't do that with revolutions, but you can do it with radians. That's why we work with radians. So the answer is 1.5 meters per second. Problem number 5, a person wishing to keep the door motionless. In other words, someone's going to be pushing on the middle of the door, someone's going to be pushing at the end of the door. We know what those forces are. This is 18.2 newtons. We know this is 34.2 newtons. So where on the door will this person down here have to push to make the door not move at all? The torques have to be equal. So the total torque is equal to 0, is equal to torque 1 plus torque 2. Let's call this torque 1. And torque 1 is going to be in the clockwise direction, so it's going to be negative in value, and this is going to be positive. Just like if someone was running south, it'd be negative, and someone's running north, it'd be positive. We apply the same thing with the torque. This torque is going to be negative, this torque is going to be positive, so I put a negative sign here. When I move it to the other side, it just becomes, add torque 1 to each side. These cancel, because one's negative, one's positive. We land up with torque 1 is equal to torque 2. Let's substitute force times radius, force 1, radius 1, force 2, radius 2. We just don't know radius number 2. I rearranged the equation. It's 21.84 newton meters. We got that from problem number 1. Divided by 34.2, which I state right here. And we land up with 0.64 meters. Notice how Newton cancels. I'm asking for a radius, and it gives me a number in meters, so I know I'm on the right track. So that's problem 1 through 5.